All right, welcome everyone. So we're doing Arctic sea ice. We'll also talk about Antarctica to some degree today. But Arctic sea ice is definitely one of the areas where we potentially see a very significant signature of anthropogenic global warming. Most obvious one is this one. This is the September sea ice in the Arctic. So September is after the summer when the area of sea ice is at its minimum. And you can see that the minimum went from 6 million kilometers squared to 3. Couldn't be simpler than that, right? 1/2. We'll see maps in a second, but this tells you that half of the minimum sea ice is gone. That's a big signal. We're not talking 5% anymore. We're talking 50%. This animation shows it very nicely, so let's see. You see in the background the sea ice during September. This is a NASA animation. Again. Okay, let me explain. So we're going to see a graph of the September sea ice annual minimum as function of time from the beginning of the satellite period until today. And in the background, you'll see images of what the sea ice looks like in September. So look at this one first. You can see that in 1978 or so, all of this area in September was covered by sea ice. Remember that. And remember this, there was just a bit of open ocean in the margins here, but basically the Arctic is completely covered, kolel this area right here, not far from Greenland. Make sense? Okay, let's see what happens later. Okay, what do you think? Is there a trend so far? Was that a yes, no? Okay, let's see.
It's going to be a yes. Oh, yeah.
2007 seems to be interesting.
Recession caused.
Yes.
2012 looks even more interesting. Look at this.
Should.
I mean,
Chicken.
Okay. Now, if you look at the background, you can see that this area that was previously completely ice covered during September is not anymore, and this area now is completely ice-free, very different from what happened 40 years earlier, right? So it's a very large signal. Question, is it because of anthropogenic climate change? We'll talk about that. We'll talk about the attribution of this signal to anthropogenic climate change and how to do it statistically today. So this is another way to look at the same thing. So that was only the minimum, right? But this is the seasonal cycle. So you can see the seasonal cycle of sea ice. There's a large seasonal cycle going if you look at this dark curve, which is the multi-year average, you can see that it's going from 6 to 16 in these units of millions of square kilometers. The dashed line in the minimum year so far, minimum year in September, and the blue line is this year, 2023. Now, even though we're below the 2012, it doesn't mean we'll be below this curve by the time September arrives, because as you'll see later, there was a very special combination of circumstances in 2012, but it's interesting that we're so far definitely below the multi-year average plus standard deviation and so on, and also definitely below the 2012, which was the minimum year in September. So this year behaves like all recent years. There's very little, there's a very significant decrease in sea ice. But the Mail Online doesn't think that way. So this says, the headline says it, and now it's global cooling. So this is an article from 2013. So let's try to understand what they're talking about. 2013 is this year right here. So right after the minimum of 2012, there was an increase. We know that things fluctuate, obviously, but I mean, look at the trend. But as far as they're concerned, this is a huge increase in sea ice, and now we're encountering global cooling rather than global warming. It's fun to look at this, don't you think? So we talked about popular press. This is a terrible example, obviously. Okay, Kevin, that's an important one. I hope you're all focused.
People come to Antarctica for the wildlife, but today on board the National Geographic Explorer, we found something spectacular. A pod of killer whales, spy hopping in the distance, narrowing in on their target, a crab-eater seal upon the ice.
Don't you feel like Kevin sometimes? Okay, this is what sea ice looks like during the transition season. So, there's in the winter, sea ice is just a very uniform cover, but during the melt season and the freezing season, it looks like that. The sea ice is made of flows. Individual flows can vary from tens of kilometers to 10 centimeters, right? And so it's a very fractal structure, if you want, because there's all scales. Look at this. I mean, large flows, very small flows. So we need to characterize such a cover, and there's several ways to characterize it. So I'd like to go through some of them. So we'll talk about sea ice area, concentration, extent, age, and thickness. It's pretty straightforward. But this would allow us to then plot these different things. So let's see how that goes. Sea ice area is pretty straightforward, right? Area is simply the area covered by sea ice in the entire Arctic. That's pretty straightforward. It's not going to be simple to observe or measure it because of the different scales, but this is what it is. Concentration. So concentration is based on the idea that we divide the area into cells. So this is the Arctic. We divide it into cells. The cells could be, say, 50 kilometers by 50 kilometers, for example. And then in each of these boxes, we measure the area. And the concentration would basically be the fraction of area in each box covered by sea ice, right? That would give us some idea of where sea ice is completely packed and where sea ice is a bit more, has more open water in it. Does everyone understand concentration? Okay. Extent is the area of boxes with concentration larger than 0.15 typically. So this gives us an idea of the general area that has some sea ice in it. Which one will be larger, extent or area? Again? Okay, other guesses? Extent. The other option is extent. Why? Because extent, so suppose I have this box is completely covered, and this box only has 20%, okay? The area is this plus the 20%. The extent is the area of both of these boxes, okay? So extent is always larger than area. But it gives us another useful measure for what areas generally have sea ice in them. Questions? Great. Age. Age is totally important. So we'll look into the process of how sea ice forms. But if you start with open water, during the winter it's going to be cold, sea ice forms, but then some of this sea ice melts the following summer, and some of it stays around and gets thicker in the following winter. And then it would be a 2-year-old sea ice, and then it might get 3 years old and 4 years old and so on, and eventually some of it would be exported out of the Arctic. So you expect to have a range of ages in the Arctic. It used to be that the ages were up to 10 years, 15 years. You'll see when you plot the data yourself soon that the age of sea ice got younger and younger. So much of the sea ice that exists right now is sea ice that is 1-year-old or 2-year-old, but that wasn't the case 40 years ago at the beginning of the satellite period. So that's age. in years. And the next one is thickness. So that could be, about a meter for new sea ice that was formed this past winter, or it could be 10 meters for ice that was that stayed around for a few years and got thicker every year. And again, we'll talk about the processes that lead to the thickening of sea ice later. So these are the ways you characterize sea ice. You can ask what the area is, what the concentration in a given box is, in a given pixel, the extent, the age, and the thickness. Any question about any of those? Okay, it's all pretty simple. And now that we know this, you can go ahead and try to plot these things, and then we can talk about why the changes happened and what feedbacks are responsible, and so on. All right, so let's see. Let's look at the results. So what do we see here? You can see the dramatic decrease in the Arctic, right? Both in the area and in the extent. You also see that the seasonal cycle is very large. So you all plotted this. Antarctica is very different. Look at that. Is there a trend? So not much. So while the Arctic has gone down by 50%, the ice around Antarctica did not. So that's something to keep in mind. And if we attribute this to anthropogenic global warming, we need to be able to explain this as well. So we'll try. Although we won't get too much into Antarctica today. Okay, so that's one. And then we talked about additional measures. So this would be the age of sea ice. So this is the age in 1984. You can see lots of reds here, red being 6 years and above. But if you look at 2018, there's hardly any red, so it's mostly 2-3 years at the most. So the ice got much, much younger. And this is another way to view it. So you could ask what fraction of sea ice is which age. So we start out in 1985. You can see all the way from 0.7 to 1, so 30% is 4 years and older, while in 2015, 16, 17, and so on, the fraction covered by 4 years old ice and older is basically 0, and same for less than 4 and 3, and we still have 2-year ice and 1-year ice. So from a large distribution of many ages, we went into basically 1 and 2 year and a little bit 3 years. That's a huge change, and as you'll see, there's a positive feedback that make young ice more susceptible to melting. So that actually makes a difference. We'll talk about that soon. And this is the thickness. The thickness used to be, see, this is in meters. So it used to be that less than 1 meter covered about 20%, and then you have from 0.2 to 0.4, so another 20% covered by 2 meters, and then a significant fraction covered by 3-meter ice, and so on. And then you had 4 and so on. But you could see that now the thickness is mostly 1 and 2 meters, but not thicker. So the ice got younger and thinner, and the area went down. So the ice is younger, thinner, and smaller area. Make sense? These are dramatic changes, right? So this is a map of the thickness, and you can see it now not just in this statistical distribution, but you can see that ice used to be very thick here, and even the yellows are 3 meters, and there's hardly any 3-meter area here, definitely no reds, so nothing about 4 meters in the present-day Arctic. Very dramatic changes. So let's talk about sea ice formation. How is sea ice forming? And that will help us understand some of these changes. So the first step is fresal ice. So this looks like, or grease ice. So these are small particles of ice floating in the water, just forming as the water temperature gets to freezing and below freezing. And then these small particles that can barely be distinguished start merging together, and we get something known as pancake ice. So this happens when the ocean is a bit wavy. The ice starts merging together. We form pieces of ice. The waves kick them around. They collide with one another. And then you get these rounded shapes that are simply the result of the collision between different sea ice pancakes, right? If the ocean is at rest, this won't happen. So this is the combination of freezing plus waves. Questions about this? And the size initially is a few tens of centimeters or maybe even smaller. And then these pancakes start merging together. So they can be even meters large. So they begin to look like this. And then eventually they are covered by snow and gets even colder, so they freeze, and then you have a uniform sea ice cover. Now, if the ocean was wavy, then the ice cover is a combination of many of these flows, and therefore the bottom of the ice would be very rough. But if the ocean was very calm, then you'll have a very smooth bottom sea ice cover. So the sea ice depends on its history. The shape of sea ice depends on its history, whether it was rough, calm, and so on. Questions? Okay, once sea ice is formed, that's not the end, because it undergoes different processes. So there's, if you have two large flows, they could be maybe even kilometers or hundreds of meters large. When they collide because currents or wind push them together, several things could happen. So this is rafting. When one flow gets over the other one, that's referred to as rafting of sea ice. And the other possibility is that when two flows collide, then you get rubble forming. The rubble forms, and then the rubble goes down and creates a keel and a sail. So this is above surface and below surface signatures of the collision between two sea ice flows and the rubble that's forming, and this is and this is called ridging. So you have rafting and ridging are the two possibilities when two flows merge together, and as a result of that, mature sea ice is never very smooth, because it underwent ridging and rafting and so on. So here's what a ridge looks like. Okay, so let's talk about the observed sea ice changes. So you just plotted it, but this is from the latest IPCC report. So you see the September sea ice, and you can see that they indicate some flat area here and some decline, and they want to point out this as being another flat area since 2012, which was the minimum. But we remember the hiatus in global temperature. These flat areas never persist. They might exist because of natural variability. So, we do expect it to keep going down. I'll show you that in a second. And you see the Antarctica one in September, so the maximum, and February, which is the minimum. And you could see some increase here, maybe not in the last few years, but for a while there was some increase in the maximum sea ice over Antarctica. And there are many explanations for that. People attribute this to ocean processes, the ozone hole, and so on. But this is something, given this significant decline, and if we want to attribute this to global warming, as I mentioned, this needs to be explained. So there are many explanations for that. So it's not necessarily inconsistent, and it seems possible, at least, that this decline is due to anthropogenic global warming, but this increase might be due to other processes. Again, possibly the ozone hole. Long story on how that's connected, actually. So I won't get into that. And then the next one is interesting too, because it shows a longer-term data set. So it used to be that nuclear submarines would get into the Arctic and measure the thickness of sea ice. So we do have some data from the earlier than the satellite period, and then there's some other sources of data that are being used. So if you look at the data even before the satellite period, which is about here, then you can see that the decline trend started in the late 1960s. The thickness got smaller, and then eventually the sea ice was thin enough that it became less robust, and it was possible to reduce the area even more using different processes that we'll talk about in a second. Okay, so a trend starting in the 1960s, maybe even before, and then an acceleration in the last couple of decades. Any questions? Okay, it's a pretty clear and dramatic signal. Okay, so now we want to cover several feedbacks that are important here. So let's make a list of relevant feedbacks. So we have the albedo feedback is clear. we don't need to elaborate on this too much. Let me just say the following. So if the sea ice declines, then there's more shortwave absorption in the areas that used to be sea ice covered and now are ocean covered. What is the ocean albedo roughly? What is the albedo of sea ice roughly? I guess. What's the maximum possible albedo? 1. So sea ice could be 0.5, 0.6, something like that. Depends whether it's snow covered, it's not snow covered, and so on. The ocean albedo is 0.1. So if once you eliminate sea ice and replace it by ocean, the ocean absorbs much more shortwave than it would have in the presence of sea ice. So that means that the ocean warms up. If the ocean warms up, this leads to more melting. More melting means even a smaller area of sea ice. So that's, we talked about the albedo feedback before, so that's a very strong one. The age roughness is an interesting one. So what happens here is the following. So suppose this is the sea ice cover. This is up. So ocean is here. And this is the ice. And this is the atmosphere here. When we get melting during the melt season, some of these patches in the sea ice would be covered by meltwater. The sea ice starts melting in the peak of the summer, and then you'll have a pool of water. So this is a melt pond. Now, because of the albedo feedback, when you have a pond, it's less bright than the ice itself. So this would absorb shortwave radiation and heat up. So this might actually create a bigger dent in the ice. Okay? And then in the next year, we'll have an ice that looks like this. So the meltwater. So now think about the following two situations. One is you have an ice that looks like this. This is a new ice with just a little bit of modulation in the surface height. And then the second one is we have older ice where the modulation of the height surface looks like that. So now if you have meltwater production, the meltwater flows into these areas. So here it will cover a large area here because this is a shallow melt pond. But the same amount of meltwater would cover a much smaller area in an older ice that has deeper areas like that. Does that make sense? So a new ice with shallow deeps would be covered by a large shallow pond, while an old ice would be covered by smaller ponds that are deeper. And as a result of that, the albedo of new ice is smaller than the albedo of old ice, because here the albedo is dominated by the melt ponds, and here the albedo is influenced by the presence of melt ponds, but the same amount of meltwater leads to a smaller area of melt ponds. So the older the ice, the more it has these changes in the depth of these areas, and therefore the smaller the melt ponds are. Let me show you a picture. I think this one would be the relevant one. So this is presumably an older ice where you could see smaller areas with melt ponds, and this is a newer ice and even newer ice. And the older the ice, the more the meltwater concentrates in some smaller areas. So you can see new ice with very shallow, very large area melt ponds. The same amount of meltwater would lead to less area covered by melt ponds. The older the ice and the bigger are these undulations in the height surface. So that means that an older ice has a rougher surface, and that means smaller and deeper melt ponds. Again, all of that is assuming that the volume of meltwater is the same. If you have younger sea ice, it's flatter, the melt ponds are larger area, and that means that it's more prone to the change of albedo by the melt ponds, and then it will melt again. Okay, so we have one feedback, second feedback. Let's see what else. Thickness mobility is pretty simple. Obviously, if the ice is thicker, it's more robust, and then when you have wind or currents, they can't move it as easily. They can't break it as easily. While if it's thin, it can break easily because of waves, and then it can be transported out of the Arctic by currents and winds. Is that a positive or a negative feedback? On melting, yeah.
Positive.
Because?
Because you're getting rid of more ice, then if there's less reflection, so it melts even more.
Okay, yeah, so if you are getting rid of ice, then when it grows again, it would grow thin, and therefore it's more mobile, and it's again prone to being exported out of the Arctic in major storms and so on. Great, so we have 3 positive feedbacks, and then there's another one that we need to cover. So that would be thickness, insulation. So that requires a bit more. Does anyone remember Fick's law for diffusion? What is Fick's law? No? Okay, we'll start from that then. So if you have, if this is temperature and this is distance, and temperature looks like this. So say this is T of x, okay? So it's warm here, hot here, and cold here. What direction would heat be diffusing to? So now you have, molecular motions and diffusion due to molecular motions and so on. People remember the reason for diffusion? Let me remind you. So suppose you have a metal rod and you heat it here. So this is meant to be a flame. So it's hot here. And as a result of the fact that it's hot, the molecules are moving faster, right? So then these molecules collide with the molecules near them, and this heat then propagates in that direction, and the molecules here begin to move faster, and faster movement of molecules means higher temperature, and this way the rapid motion of molecules spreads along the metal rod until this part is hot too. Okay? Okay. So clearly, the diffusion of heat due to these collisions of rapid moving molecules with smaller ones is going from hot to cold, right? So which direction would heat diffusion carry heat in this plot? To the right, right. So we expect heat flux in this direction. Now, what if the temperature looks like this? So this is distance x and temperature again, and the temperature like that. What would the heat flux be in this case? What would the diffusion flux be in this case? Alexandra?
None.
None. Because there's no reason for heat to diffuse anywhere, because there's no more heat in one place than another, and these random molecular motions are not going to give us any heat transport. Okay. So there's clearly a gradient of temperature here, and there's no gradient of temperature here. So it makes sense that the diffusion is somehow related to the gradient of temperature. So we can write the flux of heat is somehow equal to some coefficient times dt dx in this case. What's missing in this formula? So let's see. What is the sign of dt dx here? Is it positive or negative? If the temperature is decreasing, then the gradient is negative. So dt dx will be negative. So this is smaller than 0. The heat flux, we said, goes from left to right because it's going from hot to cold. So is the heat flux positive or negative in terms of direction? It's positive. So that means that we need a minus sign here so that the heat flux would be in the right direction. So the heat flux is equal to minus some coefficient times the gradient of the temperature. I think that's referred to as Fick's law. Would you raise your hand if you've seen this before somewhere? Okay, a few. That's great. I didn't expect you to, but it's good to know. Does it make sense, given that we're seeing this for the first time, does it make sense that the diffusive flux is proportional to minus the gradient, and then that kappa characterizes the material in which the diffusion happens. We're interested in diffusion of heat in ice. Any questions about this? All right, so continuing from there. So think about ice now. In the case of ice, we have, this is the bottom of the ice. This is up. This is the surface of the ice. So we have T surface. What is the temperature at the bottom of the ice? Well, it's going to be, because it's water, it's a water-ice interface, necessarily this temperature is equal to the freezing temperature of seawater, right? So this would be T freezing. Does anyone remember what is the freezing temperature of seawater? What is the freezing temperature of fresh water? 0 Kelvin or? Okay, funny, glad to hear it's funny. What is it? Say again?
2.
Yeah, it's minus 1.8 Celsius because of the salinity. Well done, well done. Okay. And the surface temperature of sea ice could be minus 20 easily, right? So we have a temperature gradient here. This temperature gradient is equal to the T dz. This is how rapidly the temperature changes upward within the ice. And that means that, in what direction do we expect the heat to go? Well, the water is warm and the surface is cold. So the heat flux is going in this direction, and we could write that the flux is equal to minus kappa dt of the ice dz. Okay, so this is the heat flux from the ocean into the atmosphere through the ice. Great. Now, instead of writing dt ice dz, I could approximate this dt ice dz, so that would be equal minus kappa. So I can take the temperature difference across the ice. So it's going to be minus T surface minus T freezing divided by the thickness of the ice times minus kappa. Any questions so far? So we're almost there. There's just one small equation, one additional equation that we need to cover, and we'll get to this thickness insulation feedback, which is what we're trying to understand. So now here's the idea. When sea ice grows, it grows because of this heat flux. Because think about it. The surface is cold. Heat flux is diffusing from the base of the ice upward. That heat flux comes from the ocean. This means that the ocean temperature goes down. Temperature of the ocean goes down enough, it will freeze, and you'll be accumulating additional ice layers at the base. So one way for sea ice to grow is by cooling the water at the base of the ice through this heat flux. Okay, that's a critical point. Make sense? Let me say that again. So the sea ice grows in thickness because of this heat flux, because there's heat flux from the base of the ice upward into the atmosphere through the ice. That heat flux means that the ocean under the ice is cooling. When it's cooling enough, it will freeze, and that frozen water will join the sea ice at the bottom and make the ice thicker. Great. Okay. So now that we understand that, the growth of sea ice is proportional to this heat flux. Let's write a heuristic equation for that, and that would look like this. So I'm adding some constants, so rho ice, and I'll explain these, times the latent heat of freezing for water times dH dt, h being the ice thickness. This would be equal to kappa Tf minus T surface divided by h. So I took the minus sign and reversed these two terms, but basically this is the equation we were after, so we're done with the math here. Now we just need to understand this. Okay. So the growth of ice would depend on the latent heat of freezing of the ice and the density of the ice. These two make this into a heat budget, and the heat budget, you can think about this as the heat budget for the water under the ice. And when this heat budget is influenced by the cooling on the right-hand side, this would lead to freezing of more ice and therefore to the growth of the thickness. So the important thing for us is that the thickness growth, dH dt, is proportional to 1 over h. So maybe you can now tell me, if I have thick ice or thin ice, which one, and they're both exposed to the same surface temperature, and of course the freezing temperature is the same. Which ice will grow faster, a thick ice or a thin ice? Why is that?
So whatever h is small or bigger.
So you're saying thin ice, right? Because h is smaller, 1 over h would be larger, and therefore the h dt would be larger. So thin ice grows faster than thick ice. Make sense? Okay, is this a positive or a negative feedback on ice melting? Why negative? Yeah,
We're expecting thinner ice, but the thin ice is going to grow fast.
that's right. So if the ice gets thinner, then it will grow back quickly in the next winter because thin ice grows faster than thick ice. So let's see. Again, albedo feedback is a smaller sea ice area because of some melting, leads to more short-wave absorption, and this leads to ocean warming, and the warming would lead to more melting, and this is a very, very positive feedback. And again, so this means that the reason sea ice is melting is the Arctic is because it's melting, and that refers to this feedback. So it's definitely by far the most powerful feedback around, clearly, for sea ice. Okay, so the next one that we talked about was the roughness melt pond albedo feedback. So melt ponds always accumulate during the melting season in the summer, and the melt ponds have a lower albedo, so therefore they absorb more shortwave. So the feedback goes like this. If the sea ice age declines, the surface becomes less rough. We talked about why that is the case. So the melt ponds become shallower, and therefore for the same melt water volume, they will have a larger area if the sea ice age declines. This means a smaller effective albedo of the ice because more of it is covered by melt ponds, and this leads to more melting. So again, a positive feedback on melting and making the ice younger and younger. Questions about any of these two feedbacks? Okay. So thickness insulation, so we talked about that. This is Fick's law. Diffusion being proportional to negative the gradient. We saw why that makes sense. And we replace the gradient of temperature within the sea ice by this approximation. A gradient is the temperature at the top of the sea ice minus the temperature at the bottom divided by the thickness. So we all understand that this is an approximation for the TDZ, right? Okay, great. And then we said, well, if this is the heat flux leaving the ocean through the ice, that heat flux is the reason the ice grows. So we can write this equation for the rate of growth thickness, and we decided that the HDT is proportional to 1 over h, and therefore this is a negative albedo, which means that thicker ice grows slower, or thinner ice grows faster, which is a negative feedback on melting of sea ice and thinning of sea ice. Questions about this one? All right, and the last one is the thickness mobility feedback. So if the ice is thinner, so if it's younger and thinner, then it can be broken by winds and waves more easily, and then it can be transported out of the Arctic by winds and currents. And that means that the next year would have thinner ice because this would all be new ice, which is typically thinner. So that's another positive feedback. So we have one negative feedback and 3 positive feedbacks. That was summarizing everything we did so far. Makes sense? Good. Let's talk about some of these additional things. So this is the melt ponds in first of all, just to give you an impression of what melt ponds look like, right? The sea ice is very wet in the melting season, and you can see a large-scale picture, a more local picture, and so on. And you can clearly see that the albedo of the ice here is influenced by the presence of melt ponds. This gives you a feeling for this description that we had before. We looked at this already. So this is the relation between new ice having large melt ponds and old ice having small and deeper melt ponds. So we talked about all of that. Okay. I have some slides here from Hadjo Aiken, who gave a talk here years ago, and I kept his slides because they were so wonderful. So what you see here is one of his slides. So this is the area of sea ice in the Arctic declining. You see this goes all the way to 2007, which was the first minimum. 2012 was even worse. And at the same time, you can see how the number of articles, number of mentions of sea ice in the popular press went from 0 to a very significant number. An interesting correlation there. This is the impact on indigenous communities. So you could see here animals on the sea ice. We saw Kevin before. And so this affects both animals and humans, obviously, in the Arctic. Okay, so then let's talk about projections. So first of all, the projection from I guess the one before the most recent IPCC, but the most recent one are not very different. So depending on the scenario, you have different declines, and the red is RCP 8.5. That's the business as usual, and this predicts that by 2050 there would not be much September sea ice. We already went to 50%. It's not going to be difficult for it to go all the way to 0 in September. You have some more optimistic scenarios, but you get the idea. I think this is a very iconic picture, so this is really important to know. What you see is the following. The red line is observations of sea ice over the satellite period. The black lines and the cloud and so on is climate models. And what you see here is climate models projected. So when we already knew that sea ice is declining rapidly, climate models continued predicting that sea ice would go very slowly. So they missed this level of sea ice by, this was 2012. They're predicting that the sea ice will get to this point 2050s. They missed the target by about 40 years. The climate models were too optimistic by about 40 years. This is another picture of the same thing. You see the observations getting out of the envelope of model prediction. So this is many models predicting sea ice. And we know that sea ice at that time already went down, and the models were missing that. So of course, the future generations, the modeling groups changed their models, and now they're predicting something that's more consistent with that. Whether we're getting the right result for the right reason or the right result for the wrong reason, it's difficult to tell. But I think this gives you some idea that on how climate change can surprise these models, and the models could be not sufficiently pessimistic, if you want. So I think this one is interesting. Let's do this one, and then we'll go back and talk about how do we statistically attribute changes to anthropogenic climate change. I'd like to cover one more thing today. So if you don't mind, let's leave the workshops and let's talk about the question of how do we know that the Arctic melting that we're seeing is not just a coincidence. So what do I mean by a coincidence? So you look at this time series of a model run. Suppose this happens in a climate model runs where the CO2 is actually not changing. We expect things to increase and decrease independently of that, right? Right, so you see, if you look at certain periods, you see the minimum sea ice increasing, then decreasing, then increasing, then decreasing. Overall, there might even be some trend here over a period of year 2 to year 17. There's even some trend. And then it will recover back because this is a run without any CO2 changes. So these are all parts of the natural variability of sea ice. How do we know that what we're seeing now in the Arctic is not simply part of the natural variability of sea ice? How can we tell that it's actually due to anthropogenic climate change is the question we want to answer now. So for that, look at this. So suppose we are interested in the decline over 4 years. So what we could do is the following thing. We take this long model run. It could be 1,000-year long. And we identify all 4-year trends. So you see, we take it from this point to that point, from this point to this point, from that point to that point. Any 4-year trend we accumulate. And then we find what is the probability for a certain trend to happen. Like, is this a normal trend or is this a very significant, unusual trend is the question we're asking. So we need to quantify the statistics of that. So let me describe the steps by which we do this. So this is our recipe. So detecting anthropogenic climate change in sea ice. Okay. What we're trying to do is put in perspective the trend over the last 40 years in the satellite period. We want to see, could such a trend happen spontaneously regardless of the CO2 or not? So here's how we're going to do it. We specify the interval, so number of years, over which the trend is observed. Then we take this long model run and we identify all such trends and we fit a linear line to each of these trends. Now, the fit could be done in two different ways. You could just take the initial point minus the final point, but it's actually better to fit a line to these minimum points. So do a least square fit. If you don't know what that is, don't worry about it. But if you do, then a least square fit to the minima over 4 years makes more sense. So in any case, either way, either just fitting a line to the first minus the last point or a least square fit, we can write the CS area is equal to some constant A times the year plus a constant B. That's just the equation for a straight line. So this would describe any one of these lines. Each of them would have a different A and a different B. So A is the slope, and from that slope we can get the decadal trend. So given that A is multiplying the years, so this is in units of years, the decadal trend, let's call it T, is equal to 10 times A. What does that mean? If A measures the decline in 1 year, then 10 times A will describe the decline over 10 years. That's all. Any questions so far? All right. Okay. Now we have, we calculate many such trends over the time series. You can see here 3 trends, right? But in a long time series of a model run, we could say calculate thousands of those. And then we find that the trend varies between some limits, and we bin it. What do I mean by bin it? We so bin the trends. So suppose the trends are something like this. This is T, the trend. And the units of the trend are area lost or gained per 10 years. So this would have a range of values. Say this would be the minimal trend that we find and the maximal trend we find. We divide this trend into, say, 50 bins. So that's what I mean by bin the trends. And then in each interval here, I can count how many trends like that did I get in 1,000 years of a model run, and I plot a histogram like this. So this would look like this, like this, like this. So what's plotted here is the number of occurrences of trend in each bin. And now we normalize this to get a probability distribution function. So normalize see, what do I mean by that? So I want to get a curve that looks like this. This is the trend, decadal trend just like before. This is probability. And I want to get some curve like this, approximated by this histogram there, such that if I call this the PDF of t, probability distribution function of trends, then the requirement from a PDF is that the integral from minus infinity to infinity of PDF of t dt is equal to 1. We talked about such probability distribution functions in the context of heat waves, if you remember. So in this case, it's the probability of trends. It's a bit more complicated than probability of temperatures in a heat wave, but it's the same idea. What does the PDF actually mean? It means that the interpretation of the PDF, this function, is that the probability of finding a sea ice decline trend or increase, so let's just call it sea ice trend, could be decline or inclined, in the range t to t plus delta t, and again t is the trend. So this is a range of trends. The probability is PDF, the value of the PDF at t times delta t. That's the interpretation of the probability distribution function. And then the last step is we repeat for other values of the interval length in years, say from 2 years to 100 years. Okay, so let's see what does that give us. So the claim is that this will tell us whether the current melting in the Arctic is unusual or a normal event. That's the plan. So let's see, how do we do this? But before I go there, maybe could someone, is there any question? So let me repeat the process, okay? So you have a very long climate model run. The sea ice in the climate model run goes up and down. I'm looking at this very long run. The CO2 did not change in this run. So we're looking at the natural variability of sea ice in a long climate model. And I identify trends. In this case, I look at 4-year trends, and these are the trends. You see they could be either increase or decrease. And I identify different trends. The trend is really the slope of this line. So I'm asking, is the slope positive, negative, how negative? And then I find the minimum trend and the maximum trend. The average was probably going to be 0. So 0 will be in the center of this because the sea ice sometimes increases, sometimes decreases. And then I divide this range between the minimum and the maximum into bins. And then I'm counting how many trends, in the many I calculated, so over 1,000 years, there are many 4-year trends. How many of trends did I get in each bin, which is a range of trends? And I plot a histogram like that. And then I need to normalize the histogram such that this is satisfied, that the integral is 1. And then I can think about it as a probability distribution function. Once I took this histogram and I normalized it to satisfy this, then it became a probability distribution function. I see people nodding. That makes all the difference. That's great. So, and then the interpretation, the simple interpretation of what this function PDF of t is this. The probability of finding a trend, a sea ice area trend in the range between a trend of t and a trend of t plus delta t. Remember, these are measured in millions of kilometers per 10 years, right? That probability is equal to the value of this probability distribution function times delta t. Okay. So the next thing I can do now is, okay, well, I can look at the trend in the observations. So suppose the trend is in the observations, and let me continue that right here. So here's I used this long model run and I calculated the PDF of t as function of t, and it looks like this. This is a zero trend, the positive trends and negative trends, and now I'm looking at the trend measured from observations. What happened over the last 40 years? We had a certain decline over 40 years. I can calculate the trend in area per 10 years. And then I'm asking you the following thing. Suppose the trend is right here. So it's a negative trend because we saw a decline. What does that tell me about the decline over, if this was the case? What does that tell me about the trend over the last 40 years? You take the long model run. What this tells you in these long model runs, from time to time, there's a reasonable probability that we'll get such a trend over the last, over a period of 40 years. So that means that it's not a big deal that we had such a decline, because over a period of 40 years, that happens from time to time. Let me show you what the actual result is. On the left, you see the PDF calculated from such a model run, and you see the observed trend right here. What does that tell us? Remember, the probability of encountering a trend is the value of this curve times delta t. The value of this curve at this point, at this negative trend of minus 0.7 in units of millions of kilometers per 10 years, the value of the PDF is so low that the model is telling us that in a normal integration of the model with fixed CO2, it's super unlikely to get such a large negative trend over a period of 40 years. So that means that something special has happened. What is the weakness of this argument? Maybe the model integration for a fixed CO2 doesn't show the right variability of sea ice, and therefore it shows such a weak probability. But maybe a more realistic model would have shown larger fluctuations of sea ice, even with fixed CO2, so that such a trend would not be likely. So, okay, given that caveat, that maybe the model is wrong, that's always a possibility. Ignoring that for a second, after we've clearly explained it, what this is telling us that the observed trend, this rapid decline over the last 40 years of 50% of the ice area is super unlikely to have been just a part of natural variability. People tell you climate always changes, sea ice always goes up and down, but this trend that we've observed over the last 40 years is very unlikely to happen in this particular model results. And basically every model result. So it could be that all models are wrong, but it's also possible that the trend that we're seeing is due to anthropogenic climate change. That seems to be the conclusion from that. So now you see, typically the way you do this is you say, okay, where is the 95 percentile? So here's, suppose the area under this, all of this area is 0.95. So the area here, in this area, is 0.05. If your observed trend is to the left of this point, then the probability of this change being a normal climate variability signal unrelated to any climate change is less than 5%. We're far, far beyond the 5%, as Lux mentioned, but that's how you do this. You say, well, I'm interested to know, can I attribute this to anthropogenic global warming with a confidence of 90%, 95%? You decide how far on the tail you want to be, and that's how you do this. But in this analysis, it's so far that it doesn't matter what percentage. So you can be, again, assuming that the model is not completely wrong, you can be 100% that this change that we've seen is not just a pure coincidence. That assuming about the model and so on is a big assumption, but that's what we have. We have to go with that. So what we did here is detect an unusual change. Now this change, so this is detection of climate change. The next question is, can we attribute this to global warming? That's a different issue. So in climate change, there are two issues. There's detection and there's attribution. What we did now is detect statistically without doubt pretty much that the Arctic change over the last 4 decades is an unusual change. And the next question could be, well, okay, is that due to CO2? For that, we need to come up with alternative scenarios. So maybe it's because of volcanic emissions. Maybe it's because the industrial pollution covers the sea ice in the Arctic with the black dust from coal burning, and that led to a change in the albedo, and that led to the melting of sea ice. So in that scenario, humans would be responsible for that change, but it wouldn't be the CO2, it would be something else. So that's the issue of attribution. There's detection and attribution, 2 different issues. The detection is typically easier. Here we've detected the change that is not a normal variability. The next stage is attribution. That's a bit hard. We won't talk about it too much, but I wanted you to be aware that there's detection and there's attribution. That's exactly how attribution is done. You run the model again, only with volcanoes or without volcanoes, only with pollution on the ice and without pollution on the ice. And you can use these experiments to say, okay, well, when I include pollution on the ice, this trend becomes slightly more likely, but maybe it's still outside of the 95th percentile and so on and so forth. But that's exactly how you do this. So it still relies on a model, unfortunately, but in this case, the trend is so strong that, if I had to guess, I would guess that this is due to anthropogenic climate change. I think this is again from Hajo Aiken. So this talks about the 2007 Arctic sea ice minimum, about the combination of circumstances that happened. Again, the 2012 signal, if you remember, was even stronger. So there was an unusual weather pattern, persistent winds that brought warm air and moved ice towards the North Pole. And this says that submarine data, remember I told you about the nuclear submarine data, indicated a 40% reduction in ice thickness between the 50s and the 90s. So we know that thinner ice is more mobile, and that makes it more prone to being broken and moving out of the Arctic. So the thinner and more mobile ice was more susceptible, and then there was an extreme storm that broke the ice and exported it out of the Arctic. And then there's also a claim here that warm water coming into the Arctic from the Bering Strait also contribute to thinning and breaking and so on. So all of this special set of circumstances is why there was this very strong dip at 2007 and then another one at 2012. But basically, it's all a result of the slow decline in the thickness that might be driven by CO2, is a sensible guess. We can't be sure about anything, but it seems to be a sensible guess. All right, so let's summarize the whole sea ice thing. So we see a significant melting of Arctic sea ice since 1980, possibly 70s, possibly 60s, depending on which data you believe, but the trend has been going on for many decades now. So there was a significant reduction in the area of sea ice, in the extent, in the age, and the thickness. All of these became smaller, and we now know what each of these is. In Antarctica, summer sea ice did not change much. Different sectors around Antarctica show different trend. If you look at the global sea ice around Antarctica, you don't see a change, but you see that some areas increased in sea ice areas, some areas declined, but the net did not change by much so far, so this requires an explanation. I mentioned the ozone hole. I mentioned that there might be some ocean explanations. Our focus today was the Arctic, but this is a whole story by itself that one would need to understand, and people have been thinking about this very seriously, obviously. We talked about feedback. So the important feedbacks are, first of all, the albedo feedback. And remember the saying that sea ice is melting because it's melting, which refers to the albedo feedback, which is a positive feedback. We talked about melt points and roughness and sea ice age as a positive feedback. There was the thickness mobility. And then there was the negative feedback that had to do with the thickness, which slows the bottom freezing of ice at the bottom. And then storms and wave structuring of sea ice are important, and sea ice export from the Arctic is important. So if you have thin ice and a strong storm that breaks the ice, the waves that are caused by the storm, the waves can penetrate into the sea ice field, break the sea ice, and then broken sea ice can more easily be exported by currents and winds out of the Arctic. So having severe weather events, which could just be random, they don't even need to be related to climate change, could accelerate sea ice export And that's what happens typically in these peaks that we saw before. And we talked about climate change detection and attribution. So I'd like to finish this by looking again at the animation we saw at the very, very beginning. This one. Let's just look at it again. And then so there's clearly a trend going all the way to this point, and then various positive feedback kick in, and you get these two minima, 2007 and 12, and then you have maybe a flat area, but you can only guess that it will keep going down. Any final questions about sea ice, anyone? All right, we'll see you next time.
Thank you.